Okay, class. Um, welcome back. I guess this is supposed to be after Thanksgiving. If you're watching this before Thanksgiving or around Thanksgiving break, hope your break's going well. Um, so for the last, I'm going to have two more videos. This last one is going to be on the third midterm. The material, the one after it will be not on the third midterm, potentially on the final. Okay? So these are going to be, a little bit of random topics. They're two disjoint ones. But they're things that, in both cases, I'd like you to see if you're, before you go on to 203, potentially, in the fall, or in the winter quarter. Okay, so let me tell you the definition. So we're going to talk about series today. Okay. So if we have a sequence of numbers, then you immediately can form essentially with another sequence, but we call it the series. So the series generated by the sequence is a new sequence, so is the sequence x sub k, I should call it s sub k. All right, so how is this defined? Defined by, well, the first term is the same. The second term, or maybe I should put this the other way, the second term is the sum of the first two. Okay, I'm going to put this here. The third one is the sum of the first three. And more generally, if I want the kth term to just be the sum plus x2 plus x sub k. Okay, or I'll write it from k equals 1, from I equals 1 to k of the x sub I. All right, so these terms, the x sub n, are the terms of the series. Okay, so they're the things that you are adding together, and the s sub k's are the partial sums. Okay? So we think of, that we're adding infinitely many terms together. That you have to be careful on what you mean. But what we really think of is we're adding k terms together, and then taking a limit as k goes to infinity. Okay, so we say that if the limit from k to infinity of the s sub k's exists, we say the series converges. Okay, and its value s, so this is just the limit, is the sum of the x sub k's. Okay, so I'll say some notation. So we usually write sum from n equals 1 to infinity of the x sub n is defined to be just this limit. Okay, and I'm changing notation because, well, these are the partial sums of these. Okay? All right, so now you know what infinitely many sums mean, right? There's no difference in anything that we've seen before. It's just taking the limit of a sequence, where the sequence is coming from adding the first k terms. Okay, so let me do an example. The first example, generally, if you have a sequence, is we're looking at x sub n to be 1 over n. Okay? So let me just write out the first. So n is 1, 2, 3. So the first values, right? So s1 is 1. s2 is 1 plus a half, so 3 halves. S3 is 1 plus a half plus a third, which is 1 5/6, I believe. Okay, so S sub k is 1 plus a half up to 1 over k, okay? And so when we write this sum from n equals 1 to infinity of 1 over n, this makes sense exactly when, or if and only if, the S sub k's converge. Okay? So if the sequence converges. And notice if you want to check that this is an increasing sequence, or sorry, a convergent sequence, well, it is increasing, okay, because you're adding positive numbers. So I should say notice the series is decreasing, right? The terms are going to 0, but the terms that you're adding up are increasing because you're always adding a positive number, okay? So it's increasing, so therefore monotone. So it's convergent by monotone convergence theorem if and only if the series is bounded, okay? On the other hand, it turns out in this case it's unbounded, okay? But this one's unbounded. Okay, so to show this, well, you can just take a subsequence, which is unbounded. That does it. So an unbounded subsequence is just the terms x 2 to the n. Okay? Oh, sorry, this is, I keep messing that up. This is s 2 to the n. This is 1 plus a half plus a third, all the way up to 1 over 2 to the n. And I'm just going to separate this. This is 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus 1/7 plus 1/8. And you continue this all up to 1 over 2 to the n minus 1 plus 1 plus 1 over 2 to the n. Okay? So you group, you're looking at 2 to the n terms, and you're basically cutting it repeatedly in half. Okay, so this is like the last half of the terms. Before this would be the last quarter of the remaining, then the last eighth of the remaining, and so on. Okay? So this is greater than 1 plus a half plus a half. Okay, because you have a third plus a quarter is greater than 2 quarters. Plus a half, because again, this is a fifth plus a sixth plus a seventh plus an eighth, which is greater than 4/8. Okay? So therefore, this is, and this, okay, so you do this, and then this is greater than 1 plus a half times n. Okay, because you're doing this, since you're starting at 1 over 2 to the n, you're doing this cutting in half procedure n times. All right, so this is unbounded. Okay, so that's unfortunate. The first kind of sequence that you're interested in becomes a series that is divergent, and so not that interesting. Okay, so the sum from n equals 1 to infinity of 1 over n just diverges. Okay, so let's do a better example. Okay, so the problem is, you can check with this, it's kind of a necessary condition that the terms of the sequence have to go to 0, okay? Like the things that you're adding up should go to 0 if you want to get a convergent series. The problem is that these don't go to 0 fast enough, so you still end up summing something to infinity, okay? All right, so let me do this one. Xn is r to the n, with r less than 1. Okay, and we've seen that these go to 0 quite quickly. Okay, so this should produce something convergent, and it turns out to. Okay, so the xn here generates the geometric series. Okay, so we have the sum from n equals 0, I guess, to infinity of r to the n. So 1 plus r squared, and so on. Okay? So therefore the s sub k's are equal to 1 plus r squared up to r to the k, right? And now we do our trick that we've seen before, okay, which is that s sub k, times 1 minus r, so that's 1 plus up to r to the k times 1 minus r. And then this leads to a lot of cancellation, right? Because you have 1 plus r minus r plus r squared minus r squared, and so on. And so you're left with just 1 minus r to the k plus 1. So therefore, s sub k is 1 minus r to the k sub k plus 1 divided by 1 minus r. All right? So let me just move this up a little bit. So therefore, well, now we want to look at what happens when k goes to infinity. So when k goes to infinity, this term will drop out, right? So in particular, the s sub k's are 1 over 1 minus r to the k plus 1 over 1 minus r. This just stays constant. So as k goes to infinity, this 1 over 1 minus r stays constant. And this term, now again, this is fixed. This is just some fixed positive real number. We've seen that r to the k plus 1, if r is less than 1, converges to 0. So this is constant. This goes to 0. So therefore the s sub k's just go to 1 over 1 minus r. Okay, so we get the sum now from n equals 0 to infinity of r to the n is 1 over 1 minus r. Right, so one example, one thing that we've seen before, if you plug in r as a half, this formula is saying 1 plus a half plus a fourth plus an eighth, and so on, is equal to 1 over a half, so 2. Okay, which is somewhat expected, I guess. Okay, so now what we'd like to do is, well, we know we've done a lot of work recently to kind of figure out sequences, right? So now you would like to kind of transfer that knowledge to tell you something about series. Okay, so use knowledge of sequences to say something about series. Again, since if we're taking the limit of a series, it's just you can think of it as a very special sequence, right? To say something about series. Okay, so the first one is something that I've mentioned in passing, which is called the nth term test. Again, you're kind of most interested, just when we were most interested for working out criterion for sequences to converge, you want to know that same criterion or similar criterion for when series converged. Okay, so the first one I said before already, but let's just show this, which is that if the series converges, then the xn have to go to 0. Okay, so the terms have to go to 0, and as we've seen, this isn't enough, but it's definitely a necessary condition. All right, so let me give the proof. Okay, so if the sum converges, then what you know, well, this is just saying that the S sub k's converge. All right? Now, how do we get information from this about, then, from the x sub n's? Okay, well, notice if you take the x sub k minus x sub k minus 1, of course, this is the sum of the first k terms minus the sum of the first k minus 1 terms, so it's just equal to x sub n. So therefore, we know that these terms, so the s sub k's minus s sub k's minus 1, are less than epsilon for any epsilon greater than 0 and sufficiently large k. Okay, this is, I mean, you can think of this as saying a convergent sequence is Cauchy, but that's kind of overkill, right? This is just saying if all the terms are within epsilon, say over 2 of x, of this limit, then consecutive terms have to be within epsilon. All right, so we saw that in the last homework. So therefore, well, same criterion applies here. Okay, so the x sub n, oops, and I realize that this should be, this should be x sub k, and that should be x sub k here, sorry. Then this is less than epsilon for the same k, okay? And therefore, since you're bounding this term by epsilon, this means, for any epsilon, this means that that converges to 0. Okay, so maybe I'll just write this out as well. It's just the contrapositive of this, but it's kind of a useful way to put it, right? So if the xn's do not converge to 0, then the sum diverges. Okay? Now notice this does not mean that that the sum is unbounded, right? So what you can imagine is that the terms xn might be negative 1 to the n. Okay, so I'm getting something like 1, and then 1 minus 1, and then 1 minus 1 plus 1, plus 1 minus 1. Okay, so this goes, of course, the series goes like 1, 0, 1, 0, and so on. So we don't get convergence of the series, even though it stays bounded. Okay, so let's see some other criterion, which comes from, for convergence of series, which comes from convergence of sequences. This is essentially Cauchy's criterion, which we saw. Okay, so we have the sum of the xn's converges. So again, this is a convergent sequence. Therefore, it is Cauchy. Okay, and actually, if and only if it is Cauchy. So therefore, this is equivalent to, for any epsilon greater than 0, there exists some m and n, so that if m is greater than n, which is greater than m, well then I want to say that these terms, so Sn minus Sm, should be less than epsilon. This is exactly Cauchy's criterion, but of course we can write this again as, I guess I said Sm minus Sn. Doesn't matter since we're in an absolute value, but so this is x1 plus x2 plus xm minus x1 minus x2 up through x sub n is less than epsilon. So therefore, what we end up with is just x sub n plus 1 plus x sub n plus 2 all the way to x sub m should be less than epsilon. Okay? So what this is saying is if a series converges, if I look at if I'm willing to go far enough in my sequence, and I take an arbitrary sum of consecutive terms, that has to be less than epsilon for arbitrary epsilon. Okay, and the proof is just Cauchy's criterion for convergence. Okay, but this is a useful way, again, to show that so this is useful to show series converges if the terms are not all positive. Right? If the terms are all positive, then we've seen the best tool is the monotone convergence theorem. Okay, but if the terms are allowed to be negative, then the series won't be monotone, and therefore you should look at something like Cauchy. Okay, so maybe I'll just write this monotone criterion explicitly. Okay, since I kind of said it without writing it down. So if the xn are non-negative, then these converge exactly when the partial sums are bounded. Okay, so let me do another example now, okay, which is called the P series. All right, and it's exactly what we were looking at before, so I'll sum from n equals 1 to infinity, but you take n to the p, okay, for some p in the positive reals, okay? So what we've seen is that p equals 1 is divergent, okay? Because the terms were going to 0, but not going to 0 quickly enough, okay? So let's check p equals 2, okay? So we get the sum, so it looks like 1 plus a fourth, plus a ninth, plus a 16th, and so on, okay? So it's going to be difficult to figure out what this series converges to, right? This is the usual thing, right? It's hard to tell what the limit of a sequence is, but let's show that it is a bounded series, okay? So we will show this is convergent, okay, by showing the SKs are bounded. Now again, we'll look at a subsequence and show that this is bounded. Now this you have to be a little careful of. Okay, so we'll look at a subsequence, show it is bounded, right? This is something that you can't always assume, right? A lot of unbounded sequences have bounded subsequences, but this is okay because the sequence is increasing, okay? Because the SKs are increasing. Okay, so since they're increasing, if you had a subsequence which is bounded, you're certainly going to have the whole sequence bounded, because for any term that you're interested in, you can find a further term in your subsequence which is in there and is greater than or equal to the term that you're interested in, okay? So let's say if the S sub k sub L's for some subsequence are bounded, this is equivalent to the S sub k bounded in this case, okay? So what our term is, we're going to say k sub j is 2 to the j minus 1. Okay, so these are the sums that I want to look at. So it looks like 1, 3, 7, 2 to the j minus 1. I only want to sum up these number of terms. Okay, let me put this up here. All right, so what do we get? Okay, so S sub k1 is 1. Good. Let's see what goes with S sub k2. So we're adding 3 terms. This is 1 plus 1 over 2 squared plus 1 over 3 squared. Again, we need to bound this, okay? So we want to say this is less than or equal to something, okay? And this is going to be less than or equal to 1 over 2 squared plus 1 over 2 squared. Okay, so 1 plus a half. Okay? Let's see the pattern with s sub k3. Well, this is 1 plus, well, maybe I'll say this is less than or equal to 1 plus a half, which was our first three terms, plus 1 over 4 squared, plus 1 over 5 squared, plus 1 over 6 squared, plus 1 over 7 squared. This is less than or equal to 4 over 4 squared, which is less than or equal to a quarter. Okay, so therefore, this is less than 1 plus a half plus a quarter. Okay? And this is going to be the pattern that you continue for all of these, right? So you always, for the s sub kj, you're taking something which you know is bounded, and then you're adding 1 over 2 to the j minus 1 squared, all the way up to 1 over 2 to the j minus 1 squared. Okay, so the exponent is 2 to the j minus 1. Here it's 2 to the j, and then minus 1. This is less than or equal to 1 over 2 to the j minus 1. Okay, so therefore you get that the sum, so the s sub k sub j's, I'll just say, are all less than 1 over 1 minus a half, which is 2 for all j. Okay, so therefore it's convergent. And again, we don't know what the limit is. Okay, so the limit is, well, it turns out to be strictly less than 2. Okay, so actually this, let me just say a theorem, a remarkable theorem of Euler, says that the sum from n equals 1 to infinity, 1 over n squared, is pi squared over 6. Okay? So this is a remarkable theorem. It leads to, a lot of other mathematics. So the most kind of natural proof, or I don't know if this is the right thing to say, but I'll say it. Most natural proof comes via complex analysis, which really wasn't, known in Euler's time. But the way that this naturally is proved is by looking at complex integration. Okay, so that's just an aside. Okay, so let me just give you the general picture and then state some more facts. Okay, so in general, if I'm looking at the sum from n equals 1 to infinity of 1 over n to the p, then this converges if p is greater than 1 and diverges for p less than or equal to 1. Okay, so then, and this is a useful kind of thing to know. So useful if you want to compare, convergence / divergence of other series. Okay, so for example, so if you can compare your series to something like 1 over n squared, then you'll be able to show that it converges. Similarly, you should be able, if you can compare it to 1 over, say, 1 over n, or 1 over n to the square root, then you'll be able to show divergence. Okay, so maybe I should just say the comparison theorem. Okay, which is, again, it's going to come just from comparison test for sequences. I'm going to make it simpler and just have only positive terms. Okay, so 0 is less than xn less than yn for all n, or maybe actually for all n greater than or equal to some large n. Then if the sums converge of the larger one, then the sum of the xn's converge. Right? On the other hand, if the sum of the xn diverges, then the sum of, if you add larger things, this also diverges. Again, here, divergent, since we're assuming the sums are all positive, this is equivalent to being bounded. Okay? So, for example, maybe I'll just leave this as exercises. If you take something like 1 over, say, natural log of n, for n equals 2 to infinity, what happens here? Or if I take the sum from n equals 1 to infinity of 2n squared plus 5 over 3n to the fourth plus 2. Okay, you should think about these, whether these converge or diverge, using comparison tests plus p-tests, which we know. Okay, so let me do one more example, and then I'll stop for today. So usually we've done only things with positive terms, but of course you can also take things with alternating terms, or positive and negative terms. Okay, so let's look at the sum from n equals 1 to infinity, negative 1 to the n plus 1 over n. Okay, so the claim is that this is convergent. Okay, so I'll just write out what this looks like. So s sub k is equal to 1 minus a half. Let's see, am I getting the numbers right? So 1, okay, yes, plus a third minus a fourth plus a fifth, and so on, and then plus or minus 1 over k. Okay, and to show this converges, to show convergence, we'll use Cauchy criterion. Okay, so in other words, you have to show for any epsilon greater than 0, there exists some n, so that xn plus xn plus 1 all the way up to xm is less than epsilon for all n and m less than n, or greater than or equal to n. Okay? Okay, let me pull this up a little bit. So we know what the terms are, right? So I mean, what this is saying is 1 over n minus 1 over n plus 1. Notice I don't really know what the sign is here, but since I'm taking absolute value, I can always assume the first term is positive, plus 1 over n plus 2, all the way up to 1 over m is less than epsilon. Okay, and this is plus or minus. Okay, so I claim that actually this term is less than 1 over n. Okay? And therefore we're done, and since 1 over n goes to 0, we can make 1 over n less than epsilon. Okay? So maybe I'll draw just a picture of this. So we have 0, here's our starting term, 1 over n, okay? And now, well, what is this series doing? Okay, we're subtracting a 1 over n plus 1. So we're still, this is 1 over n minus 1 over n plus 1. So we're going down 1 over n plus 1. Of course, we're staying above 0, right? Because 1 over n is larger. Then we're going up 1 over, plus 1 over n plus 1. And notice that we never are making it back to 1 over n, right? Because this is n plus 2. So we subtracted a 1 over n plus 1 and got to here. We added a 1 plus n over 2. And since, 1 over n plus 1 minus 1 over n plus 2 is greater than 0, these first three terms give me something which is less than 1 over n. Okay? And the same thing will work in general. Okay, so if I have, 1 over n, and then I'm just going to write minus 1 over n plus 1 minus 1 over n plus 2 minus 1 over n plus 3 minus 1 over n plus 4, and so on. And I might end up with a minus 1 over m or a 1 over m minus 1 minus 1 over m, depending on whether m minus n is odd or even. Okay. But in any case, we're taking 1 over n and subtracting, negative terms. Okay? So therefore, whatever this series is, so 1 over n, okay, minus 1 over m, this is certainly, well, let me say this. This is going to be less than 1 over n. What you have to be careful about is that maybe you've, subtracted enough terms so that you end up with a large negative value, and then you take absolute value, and then you get something larger. But in fact, this is also positive, right? So you can see this by taking 1 over n minus 1 over n plus 1 plus 1 over n plus 2 minus 1 over n plus 3, and so on. Okay, again, it's going to be either plus 1 over m or plus 1 over m minus 1 minus 1 over m. Okay, these are all positive terms, so you get something which is always positive. Okay, so what we've concluded is that whenever you take this sum, you end up with something which is between, so this is my sum that I'm interested in, it's less than 0 and, or greater than 0 and less than 1 over n. Okay, and since this goes to 0, the sum goes to 0 and you're done. So it so happens, again, this is, it's not, maybe I won't say a theorem, but the sum from n equals 1 to infinity, negative 1 over n to the n, is equal to the natural log of 2. Okay, so this is a lot easier than what Euler did. So you can look it up. Maybe I'll even give an explanation on the next lecture. Okay, so all right, that's all for today. Thanks.